Howdy. Good morning, ladies and gentlemen. Welcome back to another great day of internal combustion engines. Sorry for the delayed start. The audio is not being picked up by the video system, and so I had to re-record Friday's lecture as a result of that on Saturday. It's still not fixed, despite putting in an IT request. I don't know, maybe they don't start at 8 a.m. on Mondays, but anyway, I won't have time to re-record today's lecture. I also have to record tomorrow's lecture because I'm not going to be in class tomorrow. I have to leave at 11 o'clock to catch a flight out of Houston to New York later today. So I'll be recording tomorrow's lecture at the layover in Chicago so that I can have it posted in time for you all tomorrow. So I wouldn't be able to record two lectures today. So that's why I'm using my iPad here to capture the video on the board and be able to post that. So anyway, sorry for the delayed start, but here we go nonetheless. Just a couple of announcements. Number one, as I've already mentioned, tomorrow's lecture will be virtual only. I'll be out of town, so I'll have that lecture posted to YouTube hopefully by tonight in time for tomorrow morning's class. That'll be the last lecture and the last bit of material that you'll need to know for both exam number 2 as well as for lab number 4. Exam 2, of course, is this Thursday/Friday. Exam 2 will be a take-home exam. It'll be released to you on Thursday at noon through Canvas. You'll have until Friday at noon to be able to work it and have it submitted by 12 o'clock on Friday, May 6th. Okay? There will be a sample exam posted. I'll have that posted later today. And then I'll also post a video solution. There's a review session that I traditionally hold on the reading day, Wednesday, but of course I'll be out of town, so I won't be able to do that in person. And so I'll have that review session posted for you later on today as well. And so you can review Friday's lecture, today's lecture, and tomorrow's lecture along with that review session going over the sample exam, and you'll be very well prepared, I think, for exam number 2, okay? You won't have to do any combustion equation calculations or equilibrium equation calculations, any of that material that we've covered since the first exam. There'll be some questions on there, for example, how do you interpret the change in efficiency, for example, or how do you interpret the change in power? And as always, you want to rely on your equations to help explain those trends as much as possible. So if I ask you a question will this engine make more or less power, or why does it make more or less power, whatever it might be, you want to go back to that power equation to be able to substantiate your answer. Okay, even if your intuition is correct, if you don't substantiate it using the equation, then that's not good engineering. Okay, good engineering is both intuition as well as relying on the fundamental science. Okay, and so you need to make sure that you rely on that equation, which is substantiating your intuition. Because quite frankly, as practicing engineers, there's going to be times when our intuition is incorrect. Okay, and that's when we have to rely on the fundamental science and math to be able to make sure that we're making the right decisions. Okay, so that'll be your exam number 2, and then of course lab number 4 is due Monday evening at 11:59 p.m. Okay. Any questions before we get started? All right, very good. So there were a couple of questions on lab number 4 that I wanted to address, and they're both related to the brake torque versus the indicated torque. And I'll respond to those emails as well, but for the brake torque, that brake torque data is given to you in the lab file. Okay, so that one is pretty straightforward. The indicated torque is what you will calculate off of the measured cylinder pressure. Okay, so much like you did way back with homework number 2, and you were given that Excel spreadsheet, and you had to calculate the IMEP, the indicated mean effective pressure, you'll do the same thing with this set of pressure data that you have, where you calculate IMEP, and once you get IMEP, from that you can determine your indicated torque. Remember that mean effective pressure is work divided by displaced volume. So IMEP, indicated mean effective pressure, is indicated work divided by displaced volume. And then of course there's a direct relationship between indicated work and indicated torque. Okay, and so once you calculate that IMEP value from your pressure data, you'll be able to calculate the indicated torque. Okay? All right, so let's pick up where we left off on Friday. And so on Friday, if you remember, we basically were drawing our brake torque as a function of spark timing, theta s, right? And I can't remember exactly where I put TDC, but for today's discussion, we'll go ahead and put TDC over here on the right-hand side, because there is one point of clarification that I want to make, and that is that when we are plotting a parameter like brake torque as a function of a crank angle resolved parameter like spark timing, this is different than if we were plotting, say, cylinder pressure versus the cyclic resolved crank angle resolution. In other words, these are crank angle degrees that we have on this x-axis, but these are for individual steady state operating points of the engine where it's operating cyclically, right, cycle after cycle after cycle, and this just happens to be the spark timing for every single cycle that we measure that data point, right? So this spark timing here, this might be, say, 45 degrees before top dead center, and when the spark timing is set to 45 degrees before top dead center, this is the torque value that we get. And if we retard our spark timing by, say, 10 degrees, and now this is our spark timing at 35 degrees before top dead center, lo and behold, we happen to get a higher brake torque at that later spark timing, okay? So I just wanted to make sure that that was clear, that when we plot this as a function of theta, this is different than when we're plotting, say, cylinder pressure as a function of theta, where that's a cycle-resolved crank angle resolution, okay, where we're literally marching through the cycle, reporting the measured pressure at every crank angle of that particular cycle, okay? Okay, so then we also established the fact that, of course, there's a peak point here, which we call the MBT, right, the maximum brake torque, and there's also a corresponding spark timing that results in that MBT, theta MBT, that maximum brake torque spark timing, okay? And we started to talk about why torque is low when we're advanced of the MBT timing, and why torque is low when we're retarded from the MBT timing. And we said that on the condition when we're advanced of the MBT timing, we said that we had an issue of, and I put it in quotes, expansion loss, and a better way to say that would actually be a combustion phasing loss. And we're going to talk more about this here in just a little bit to provide a little more detail to that. Okay, in other words, we have a combustion phasing issue. We've phased combustion to occur too early in the cycle where the compression of the piston is still moving up, and basically that's working against us to some extent. Now, there's a lot of clarity that needs to be added to that statement, so we'll get to that in just a moment. But the second issue, of course, is that we also have increased heat loss. So because we are increasing the pressure and temperature of the mixture, both due to an advanced phasing of combustion, but also because that piston is moving toward top dead center during that compression process, we have elevated temperatures and pressures in the cylinder, thereby increasing the extent of heat loss that we have. Now, when we're retarded of that MBT timing, at that point, it's only a combustion phasing issue, right? And so we really only have what we would call expansion losses when we're retarded of MBT. But again, to be clear, this again is just another combustion phasing issue, okay? Okay, so let's talk about this combustion phasing, right? If you remember, when we did lab number 2, part of the reason why we had you evaluate the difference between the constant volume cycle and the constant pressure cycle is so that we recognized that it's ideal, thermodynamically, for all of the energy to be released right at top dead center, right? We want all of that energy to be released right at top dead center when we're at the minimum volume, and all of that energy gets released at that single moment in time, right? So, and the reason why, if you remember from lab 2, is because you then have that opportunity to expand that added energy through the full expansion stroke, right? That expansion stroke is where the work transfer takes place, and so we want to get all of the energy in there at that moment so that we can expand all of that energy through the full expansion stroke. Well, the same concept applies to real combustion. Even though we recognize that we can't have that real combustion process take place instantly like that, we already established that on Friday, we still want combustion to be phased appropriately so that we're maximizing that expansion stroke as much as possible, okay? And so if we have combustion, and so to describe this, what I'm going to do is I'm going to go back to our PV diagram, and I'm going to draw three situations, right? One where we'll get low torque because combustion occurs too early, one where we'll get the maximum torque because it occurs right at the right spot, and then one where we get low torque because combustion occurs too late, okay? So in the first case, right, so we have, of course, our ideal situation where we have all of the energy released right at top dead center. And so you already know this one, right? We have our compression process through the compression stroke. We go all the way to top dead center. And then at that one moment, we release all of our energy, and then we're able to expand through the full expansion stroke, right? So in other words, releasing all of the energy at one moment in time at top dead center is going to give us the highest amount of torque, okay? Okay, now, if combustion occurs too early, what might that look like on the PV diagram, and how does that translate into lost work, okay? Well, in that case, we're going to start at our, so this is the too early case. Again, we'll have our compression process, but now, because combustion is occurring too late, and just for simplicity of this example, I'm going to assume all of the energy releases at one moment in time. So it's still going to be constant volume combustion. It's just going to be constant volume combustion early of top dead center, okay? And so we have our compression process, and then we release all of our energy, right? So we have constant volume combustion. Our pressure immediately rises at that one moment, but the piston still has to move to top dead center, right? So we still have to get this piston up to top dead center to follow the kinematics of the crank slider mechanism. And so we've added all of our energy, and we've increased the pressure now up to the pressure at top dead center. Well, now what happens? Well, the piston just reverses direction, and because we're assuming this was isentropic compression, and we're going to follow isentropic expansion, the pressure is just going to follow along that same curve as it expands now toward bottom dead center, okay? And now you can see where there is lost work, right? This whole region right here is the lost opportunity to do work because we had combustion occur too soon, okay? And so this shaded area that you see here is lost work due to too advanced of combustion. The reason why I highlight this, and we're going to go over the too late combustion in just a moment, but that one doesn't seem to run into debate in, the scholarly circles of IC engine research. Many people will say that this effect is not real, that this reason in the drop in torque as you go to too advanced of timing is not influenced by this quote-unquote expansion loss because the energy that you put into pressurizing the mixture, you get right back out of the expansion. Well, that is true, but you're still failing to see that there's this section of the PV diagram where you have lost work. Where you remember, work is area under the PV diagram. So if I minimize that area, I'm decreasing the amount of work I can get out of that cycle. So there is absolutely a real thermodynamic loss if combustion occurs too early that is above and beyond the increased heat loss, which is also, of course, a very real phenomenon, okay? Okay, so what happens if we go to too late of combustion, right? It's going to look very similar, but in the case of too late of combustion, now what we will have, again on our PV diagram, we will have our compression stroke, and because it's too late, we're going to go all the way up to TDC along our compression stroke, okay? And again, we're releasing the combustion process occurs too late, so we go all the way up to TDC, and we actually start to expand the mixture until combustion finally decides to take place. Let's suppose it's right here, and then we have our combustion process, and then we follow our expansion, okay? And so this is the situation where combustion is phased too late, and once again, you can see that there's a lost work opportunity, right? This area in here basically represents the lost work due to combustion occurring too late. okay? So spark timing is what's directing this phasing of the combustion process, right? Nothing can start in an SI engine until that spark releases. Once that spark releases, now we can get into how we actually model these two periods of combustion, the flame initiation period and the rapid burning period, which we're going to start here in just a moment, okay? But before that can even happen, that spark has to release, and depending on when you release that spark, it's going to change your phasing of combustion and correspondingly have this effect on your brake torque, okay? Okay, so we can take a look at what these different curves look like for different spark timings. And so this is from your Chapter 6 notes. This is slide number 6. And you can see, of course, where we have here our it's the relative torque, right? Just so that you know what relative torque is, that's essentially where we take the peak torque and we divide any given torque by that peak torque, okay? So engine manufacturers will very often do this because they actually don't want to reveal how much torque their engine is making. So they themselves know what the peak torque is, and then when they report data, they'll normalize it by that peak torque and indicate what the relative torque is, okay? And so what this curve is telling us is this is basically showing what the torque behavior as a function of spark advance is, okay? And so now we have to be a little bit careful here because what's happened is the x-axis is now degrees before top dead center moving from left to right, which is a little counterintuitive to how the cycle actually goes. When I drew the brake torque, I drew it so that spark advance was moving from right to left, okay? And so in this case here, the spark advance is 10 degrees. That's basically saying 10 degrees before top dead center, and then 20 degrees before top dead center, 30, 40, so on and so forth, okay? And then you'll also note that we have the maximum brake torque identified on there, right? And so that's what they're normalizing their brake torque to, is that maximum brake torque, okay? And as you go to a retarded timing, which again is going to the left in this figure, then we have a decrease in our torque, again because we have that expansion loss that's associated with having combustion being phased too late in the cycle, okay? Now how this actually translates into the pressure diagram is shown on the left-hand side. So this is showing you the cylinder pressure now as a function of the cycle resolved crank angle, right? So this is actually showing you the cycle resolved data rather than the steady state operating condition data, like is what is shown in the figure on the right. And you'll notice that there's 3 different spark timings that are shown. There's the pressure data that results from a spark timing of 10 degrees before top dead center, 30 degrees before top dead center, and then 50 degrees before top dead center, okay? And what you'll notice, of course, is that we go to higher and higher or more and more advanced spark timings, the pressure data tends to get very steep and also go to very high pressures, okay? So when we're at 50 degrees before top dead center, the torque value is not even shown on the spark advance plot on the right-hand side, right? 50 degrees would be somewhere out here, and you can imagine that the brake torque is somewhere very low relative to the MBT spark timing, which is roughly about 33 degrees, right, based on this plot. And you can see that the 30 degrees is listed here, the 30 degree spark timing, and you'll notice that the pressure data looks a little more healthy in terms of phasing that pressure correctly during the cycle, okay? And then of course if combustion is too late, where now you have a spark timing of 10 degrees before top dead center, even though the spark released 10 degrees before top dead center because it takes so much time for combustion to get going, we begin to actually see a decrease in the cylinder pressure, right? So the piston comes up during compression, reaches top dead center, where roughly you reach peak pressure at top dead center, and then the pressure actually begins to decrease a little bit as the piston is now moving back toward bottom dead center, expanding the mixture and causing the pressure to drop. Combustion then finally catches up and takes over, and then causes another rise in pressure as a result of combustion, and then begins to follow the expansion stroke, okay? So you can see one of the important things to note here is that where MBT timing occurs, you'll notice that the location of peak pressure, that's an important parameter that we'll talk about the rest of today and tomorrow. The location of peak pressure when you have maximum brake torque timing is going to be somewhere around 20 degrees after top dead center. Okay, do you see that? How the location of this curve, right? So this 30-degree timing curve is roughly close to where MBT timing is, and the location of peak pressure is about 20 degrees after top dead center. Okay, and so that sweet spot for location of peak pressure is usually somewhere between 15 to 20 degrees. Okay, so for example, oftentimes I'll have people ask me, can we use your dyno to do brake engine testing on our engine? And because we want to calibrate the engine and find brake torque and things of that nature. And oftentimes I'll say, well, if you have access to your cylinder pressure, which is not always the case, but if you have access to your cylinder pressure, you can get yourself pretty close by just looking at the location of peak pressure, right? If you can determine where your location of peak pressure is, you actually don't even need to put the engine on a dyno. You can just monitor that cylinder pressure and see where your location of peak is. And if you're 5 degrees before top dead center or after top dead center, you're way too early. And if you're 25 degrees after top dead center, you're way too late. You want to kind of get your location of peak pressure somewhere in that sweet spot of 15 to 20 degrees. Okay, and so that's usually a good rule of thumb, if you will, in terms of being able to do that. Okay, all right. So let's now dive a little bit deeper and start to understand what are the things that can actually influence the flame initiation period and the rapid burning period when we actually release our spark and begin to have that combustion process. Okay, so the way for us to set up this model is to think about what are the things that affect the flame initiation period and what are the things that affect the flame development period. Okay, so let's first of all talk about the flame initiation period, right? So remember that flame initiation period or what we call delta theta D, okay, compared to delta theta B, which is the rapid burning period, okay? Again, you'll just as a reminder, this delta theta D, the flame initiation period, this is the time between spark release or theta S and 10% mass fraction burn or theta 10. So delta theta D is equal to theta 10 minus theta S, okay? Okay, so what's kind of nice about the flame initiation period, okay, is we can predict how long that flame initiation period is simply by knowing the laminar flame speed of the fuel-air mixture, okay? The flame initiation period is most strongly governed by the laminar flame speed of the fuel-air mixture, okay? So delta theta D, flame initiation period, is most strongly governed by the laminar flame speed of the fuel-air mixture. So, if I know the trend of my laminar flame speed of the mixture, the fuel-air mixture, this is a property of the fuel-air mixture. We're going to talk more about it here in just a minute. If I know the laminar flame speed of my fuel-air mixture and I know the trend that it's going, then I can predict what my delta theta D is. I can predict what my flame initiation period is, okay? So let's talk a little bit about what that laminar flame speed is. So laminar flame speed, it's a pretty easy concept. It's obviously telling us the flame speed under laminar conditions, right? So imagine that you have a tube, and suppose there's a little spark source in this tube, and this tube is filled with a fuel-air mixture. And I release a spark, right, at some time t equals 0. And what will happen is a flame will establish that, assuming I design my experiment correctly, that flame will travel the length of the tube, and so long as I don't allow it to transition into turbulence, the speed of that flame is going to proceed laminarly, okay? And so, again, I have to be real careful that I design my experiment carefully, because it's super easy for a fuel-air mixture when it's burning to trigger into turbulent reaction, okay? But as long as I can keep that flow laminar, then the rate at which this flame moves through this tube can be modeled as a laminar flame, okay? And so that speed that it travels through that tube, right? I know what my distance is, for example, and I know how much time it takes to get from time t equals 0 for the flame to reach the end of the tube. I can then calculate and measure, what my laminar flame speed is, okay? So that's basically what laminar flame speed is, and much of what we talk about with flame initiation period as well as the rapid burning period is going to be strongly influenced by this laminar flame speed, okay? So what affects laminar flame speed, right? Well, let me back up a minute, okay? So first of all, in the context of flame initiation period, a higher laminar flame speed, which I use S sub L to indicate laminar flame speed, will result in a shorter flame initiation period. In other words, it takes less time to do that whole flame kernel development from release of spark to 10% mass fraction burn. That period gets shorter, things happen faster with a higher laminar flame speed. So a higher laminar flame speed will result in a shorter flame initiation period. Okay? So if I can somehow accelerate my laminar flame speed, I can decrease the time that it takes to do that flame initiation period. Okay? Okay, so let's talk about then what actually influences that laminar flame speed. So there are several items or factors that affect laminar flame speed. Okay, and I have them all listed here. Okay, the first is fuel type. So for example, if I have a hydrocarbon fuel, pretty much all of my hydrocarbon fuels all fit within the same family so that the laminar flame speeds are more or less very close to each other, right? They might be within 20 to 30% of each other, okay? Your various, from methane up to diesel fuel, right? Laminar flame speeds might only change by maybe 20 to 30% at most, okay? But then if I go to a non-hydrocarbon fuel, like hydrogen, H2, well, now we're talking about factor differences, right? Where the laminar flame speed of hydrogen might be 2, 3, 4, 10 times faster than the laminar flame speed of a given hydrocarbon fuel, right? I've changed families of fuel. I've completely changed the type of fuel I have, and so I have a drastic change in my laminar flame speed, okay? So that's number one. Number two is fuel-air equivalence ratio. what's really cool about laminar flame speed is it scales with temperature of the reaction. The higher the temperature, the faster the laminar flame speed. It kind of makes sense, right? It wants to move through faster. It's already got energy to help it move through, to help the flame move through the mixture faster, right? So what's interesting is if you remember where peak adiabatic flame temperature occurs, right? It occurs slightly rich of stoichiometric for most hydrocarbon fuels. Well, that's exactly where peak laminar flame speed occurs, right? So you can assume that your fastest flame temperature is going to be slightly rich of stoichiometric, and if you go too lean, it's going to slow down, and if you go too rich, it's going to slow down, right? So that's, and we'll draw that figure here in just a moment, okay? Another effect is the unburned gas temperature, right? It's somewhat related, but if I increase my gas temperature, then I'm going to increase my laminar flame speed, okay? That's contrary to unburned gas pressure, where if I increase my pressure, you can kind of think about it in terms of there being a certain number of moles in the mixture, right? So if I have a given, say, tube, right, with a fixed volume, and I keep my temperature the same, but I increase my pressure of that tube, right? Maybe my original experiment was at 1 atmosphere of pressure, and I increase it now to 2 atmospheres of pressure, same volume, same temperature. Well, the only way I can do that is by adding more mass, by adding more moles, right? Well, just like when you're trying to walk through Kyle Field on game day and there's a lot of people there, you just can't run through the ramp. You have to kind of walk as a group, right? The more people there are, the slower you're going to walk. It's the same idea with the laminar flame speed, right? If there's more moles in that mixture, right, that flame is going to move slowly, more slower. Less fast through that mixture than if you had fewer moles at a lower pressure. So you raise the pressure of the mixture, that's going to slow down your laminar flame speed. Okay, so that's item number 4. And then finally, the other effect is the level of exhaust gas recirculation. And again, you can think back to what we studied when we looked at adiabatic flame temperature. Whereas we raise the EGR level of the mixture, the flame temperature comes down. That correspondingly is also going to have an effect on laminar flame speed, whereas you raise the EGR level, that's going to have a tendency to lower the temperature of the reaction and therefore lower the laminar flame speed. Okay? Okay, so we can capture a lot of this information by looking at data, right? And again, this data is provided for you in your notes, okay? And so the first set of data that you see is the effect of fuel type and fuel air equivalence ratio on the laminar flame speed, right? So let me just kind of walk you through this a little bit. The first thing you'll note is that they refer to this as burning velocity, okay? So the reason why they refer to it as burning velocity as opposed to flame speed is because, in many cases, the mixture is just burning. It's not necessarily having a propagating flame that's moving through the mixture, okay? So don't let that hang you up. Laminar flame speed and burning velocity in this context can conceptually be taken to be the same idea, okay? But then you'll also notice that we have this burning velocity, and it's as a function of fuel air equivalence ratio. And so, of course, our stoichiometric case is right here at 1, right? And you'll notice that if we just pick one fuel, for example, let's say propane, C3H8, you'll notice that its peak laminar flame speed occurs slightly rich of stoichiometric, somewhere at about 1.1, right? Which again is right about that point, that fuel air equivalence ratio, where maximum adiabatic flame temperature occurs, okay? So if you know what the temperature of your reaction is going to do, you have a pretty good idea of knowing what your laminar flame speed is going to do, okay? And as we go lean, then our laminar flame speed decreases, and if we go rich, then our laminar flame speed decreases, okay? Okay, now also embedded on this plot are the laminar flame speeds for several different types of fuels. So we have, of course, methanol, which is C3H0H. It's basically the alcohol version of methane, okay? We have propane, which is one of our standard normal hydrocarbons, C3H8. We have gasoline, which of course is a mixture of several different types of hydrocarbons that we actually don't know what necessarily is in it, right? It's just a big soup of hydrocarbons. We have our good friend isooctane, C8H18, and then of course we have our best friend methane, CH4, right? Which we've traditionally used as our combustion reactions in our lecture periods. And so you'll notice, right, the scale on this doesn't really change all that much, right? So if we go from a fuel like methanol, which has a peak laminar flame speed of about 43, and we go down to something like, this one is isooctane, which has a peak laminar flame speed of about 33, right? You know, that's a difference of 10, which is in that 20 to 30% ballpark that I had mentioned, right? Now, if I were to plot hydrogen on this curve, you wouldn't see it, because the laminar flame speed of hydrogen is somewhere on the order of 200 to 300 centimeters per second. Okay, it screams. Hydrogen is a super fast reaction, small molecule, high adiabatic flame temperature. One of the reasons why hydrogen is dangerous is because it has no mercy. Okay, when it ignites, it's gone and it's off for the races. Okay, it's very difficult to control hydrogen, and so its laminar flame speed is much higher than any of these ordinary carbon-based hydrocarbons. It's carbon that's slowing the laminar flame speed down, right? And you can kind of see that a little bit when you look at, say, something like methane versus isooctane. Propane is a little bit higher because without getting into a lot of the details, but there's a transition as you go from methane to propane to then heavier hydrocarbons, okay? Okay, now on the plot on the bottom, you can see what the effect of unburned gas temperature and unburned gas pressure is on laminar flame speed. So again, we have the laminar flame speed on the y-axis, and then we have the unburned gas temperature on the x-axis, okay? And now there's two sets of data. There's actually 4 sets of data on this plot, okay? And it can be a little bit confusing, so let me just kind of walk you through it. First of all, there were 2 sets of experimental measurements taken. There were the first set that were taken by Charles Westbrook and Fred Dreyer out of Princeton, and then there was Medgalchi and Keck taken out of MIT, okay? Neither one of them are probably correct, right? Princeton, MIT. You know, we need Peterson's group from Texas A&M on here giving us some data, but this is all from the 1980s, so we'll just have to go with it, right? But of course, what you notice is that as we increase the unburned gas temperature, our laminar flame speed increases, okay? Which is exactly what we would expect to have happen. So for both, you know, of course, Westbrook and Dreyer and Medgalchi and Keck, right, as we increase the unburned gas temperature for both sets of pressure data, I'll get to that in just a moment, we see the laminar flame speed increasing, okay? Now, we also see the effect of increasing pressure. So the solid lines for both research groups is at a pressure of 1 atmosphere, so that's this set of data here. And then the second set of data is at a pressure of 10 atmospheres, right, which is the second set of data, the dashed line data, again, for both sets of researchers, right, for both research groups. And what you notice, of course, is that as you increase pressure, you decrease your burning velocity, right? So if we just happen to pick 500 Kelvin, for example, the laminar flame speed when we're at 1 atmosphere is almost 100 centimeters per second, but as we increase the pressure by a factor of 10, we drop that laminar flame speed down to about 60 centimeters per second for the same temperature. Okay, so again, that increased pressure effect has a tendency to slow down your laminar flame speed, okay? Okay, so that's the effect of fuel type and fuel air equivalence ratio. Now, at this point, what I'd like to do is take a small segue and just let you know that one of the things you're going to be doing on exam number 2 is you're going to be making an analysis, a comparison between one engine type and a second engine type, where you're going to have to diagnose what the effect on laminar flame speed is. So you're going to have to think about, okay, how does this change to my engine change the unburned gas temperature? And how does it change the unburned gas pressure? And how does that change the adiabatic flame temperature? And how does that, does my fuel change, or am I using the same fuel? And I have to take all of that information and I have to translate it to, okay, my net effect on the laminar flame speed is my new engine is going to have a faster laminar flame speed. Or my new engine is going to have a lower laminar flame speed. Or my new engine is going to have the same laminar flame speed. Okay? And you're going to have to basically use that analysis, and use your judgment to decide what happens to laminar flame speed. And then once you know what happens to laminar flame speed, well, then you can decide what happens to the flame initiation period. If the laminar flame speed is higher, flame initiation period will be shorter. In other words, the time between spark and 10% mass fraction burn becomes shorter. If you decide that laminar flame speed is is lower, then that means that your flame initiation period will be longer, meaning it takes more time to get from spark to 10% mass fraction burn. And of course, if you decide that laminar flame speed is the same between the two engines, well, then there's no effect, right? The flame initiation period between the two engines is the same, okay? So I'll be walking you through that exercise with tomorrow's lecture, as well as during the review session, right? That's why it's important to watch the review session, and you'll get a feel for how you can do that analysis, okay? Now, I'll tell you right now, and I'll try to remind you again, but invariably, students will always ask me, you know, these differences are very minor, right? Like, what if I, do the analysis all correctly and I trend it all the right way, but when I go to look to see what the effect on my laminar flame speed is, I show that it's higher, but you said it was the same. No worries. So long as your analysis is correct and you do the correct trending, then no problem, right? That's easy to dispute, okay? But if in your analysis you say that the higher pressure of the new engine causes the laminar flame speed to be faster, well, that's a problem, because that's contrary to what we would expect, okay? So don't let that part bother you. Exam number 2 is going to be a very unique exam that you'll take as an engineering student, because there's actually very few, if any, calculations that you're going to do, okay? It's all going to be based on how you interpret the data, and how you draw conclusions from that data, and how you can make decisions based on that analysis. Which, by the way, guess what? That's what you all as Aggie engineers are going to be doing in your career, okay? They're going to let the number crunching be done by somebody else, most likely a computer. What they need you to do is to look at that data, analyze it, and make a decision on it, okay? And that's where very skilled engineering starts to come in, okay? Okay, so these are some of the effects on laminar flame speed, right? But if you remember, there's an additional effect, and that's the effect of EGR, okay? And as we've already indicated, what you can see on this plot, for example, is we have laminar flame speed of the mixture divided by some laminar flame speed of the reference condition. Again, they're trying to conceal the data a little bit here, so they're normalizing that laminar flame speed. And you can see basically that as we increase what they call the mole fraction diluent, X sub B, that would be the burned gas mole fraction. So as you increase the burned moles, right, the number of burned moles in the mixture, that is, as you increase your exhaust gas recirculation level, your laminar flame speed will have a tendency to decrease, okay? And that's exactly what we're showing here, okay? Okay, so that's the effect of laminar flame speed, the various things that are affecting laminar flame speed, and the ultimate effect on flame initiation period. What we'll pick up with for tomorrow's lecture, the last lecture, which again is only going to be a video lecture, is to now talk about the rapid burning period. Okay, and the rapid burning period is entirely a function of what we call turbulent entrainment. If you were to look at those laminar flame speeds and you were to say, okay, my laminar flame speed of the mixture is 45 centimeters per second, and my cylinder, my stroke is, say, 5 centimeters. If I rely strictly on laminar flame speed, knowing my stroke length, there's absolutely no way I would be able to burn this mixture laminarly within the very short amount of time that my cycle is giving me. My cycle is literally giving me 10 or 15 milliseconds to complete this combustion process, and I've got too much space at such a low laminar flame speed to be able to complete that combustion process. But we don't need to worry, because once that flame initiation period is done, then that mixture gets engulfed with a turbulent entrainment, and so I can basically rapidly spread my flame throughout the whole mixture very quickly, and then burn up the mixture with the amount of time I have available as governed by the cycle. Okay, so we'll pick up Tuesday's lecture with that discussion and then conclude the semester. Thank you all so much for coming to class, and I won't see you again in person, right? And so if you have any questions, I'll be back in town on Friday. We can set up times to meet, or you can send me emails, what have you, and of course I'll be around town late next week as well. Thank you all for coming to class. Have a great day.
So the ambient gas temperature, that's like...
Let me just stop this real quick. Let's see.